Today we're going to talk about molecular structure and reactivity as applied to substitution and elimination reactions. So we're going to be studying, if we are going to be studying, say, SN2 reactions in its competitive reaction E2, and also SN1 and the competitive reaction E1, so substitution elimination. The first thing that we need to review is the structure of the substrate. So we have something like this, an alkyl halide. So factors that we need to know to determine what is the mechanism and predict products. So we need to know the structure of the substrate. So, and see what that is. So if we have something like this, say, the carbon where the bromine is, we're going to call that the alpha carbon. And since we have here at the alpha carbon only one R group, this is a CH2, right? One R group, we're going to call that a primary alkyl halide. So now if you have something like this, and now, no, it's going to, I added one more carbon that I wanted. Say that I have here a bromine. Now, this, remember, with the leaving group, in this case, the leaving group is bromide, right? It's going to depart as bromide when it goes. But this is your alpha carbon, and you see that at the alpha carbon, you have 1 and 2 R groups, so that's a secondary alkyl halide. And finally, if I have this pattern, this structure, and I have 3 different R groups, different or the same, never mind, but 3, this is my alpha carbon. We have here a tertiary alkyl halide. Notice that at the primary alkyl halide, I have 2 H's here, this is a CH2. At the secondary, I only have 1 H at this carbon, and here I have none at the tertiary. So knowing the structure is very important. When we are studying this reaction, there's something also very important, which is the leaving group. So typically, good leaving groups are, for example, iodide, bromide, chloride. These are weak bases, so stable, weak, amazing, weak bases, good, excellent leaving groups. And remember that these come from a very strong acid, so hydroiodic, for example, very strong. So these are stable, so they are good leaving groups. This type of reaction happens also in other, say, substrate, not alkyl halides, with different leaving groups, such as alcohols. But then we need to study how to make OH a good leaving group and under which conditions we will do that. But for now, we're going to be talking about alkyl halides. So we have the structure of the molecule that is going to be undergoing that reaction. We have the leaving group, and also we need a nucleophile or base, and that is very important. So I'm going to erase that. I'm going to keep the substrate. So for the substitution reactions, we need obviously 1 nucleophile. And nucleophiles can be different, so we can have neutral nucleophile, but say you have some electron density to it, or charged species. For example, we can have here water. An example of that, we can have hydroxide. Here, hydroxide is much stronger nucleophile, and it's also a strong base. So we're going to say this is strong base, strong nucleophile. Water, on the other hand, is a weak base, weak nucleophile. We're going to be using those terms to actually help us when we are determining what is conditions in products. But say, for example, that I have now dihydrogen sulfide. So remember that sulfur is right underneath oxygen in the periodic table, group 6A. And this is the acid and its conjugate base, this hydrogen sulfide, like that. Now, this is now a much stronger nucleophile. That's a strong nucleophile. This molecule now is much more acidic. Here I want you to see the pKa, for example, of water is 15.7, whereas the pKa, first pKa of the hydrogen sulfide is 7. So much stronger acid, so much weaker base. But it is a weak base, but it's a strong nucleophile. And the fact that it's like that is because sulfur is much bigger, larger atoms tend to be more polarizable. So right there is the trend when we are in a group. So going down in the periodic table, as the orbitals get bigger, they are more polarizable and therefore better nucleophiles. So similar to that, let's say, let me erase on this side to give you another example in trends. And typically, when you are in another group, say for example, you have hydroiodic, this conjugate base is iodide, hydrobromic, conjugate base is bromide, and hydrochloric acid, this is a conjugate base. So here, the stronger acid is hydroiodic, that's a weaker base, but it is weak base, it is a strong nucleophile. And the fact that it's a strong nucleophile is because, again, it's much larger, say, for example, the chloride. So size is increasing this way, and so is increasing the nucleophilicity. So there are, here we're going to be then to determine what is the preferred mechanism. Again, we're going to be looking at the structure of the substrate and the nature of the leaving group, the nature of a nucleophile, and we have talked a little bit about that. And another factor that is important is the solvent.